Relativity is the branch of physics that was discovered by Albert Einstein. There are two sort of subdivisions in relativity called special relativity and general relativity. And special was discovered in 1905, and then in 1915 he discovered general relativity. Basically, they're the branch of physics that deals with the unusual effects that happen when an object travels at very, very high speeds or in a very intense gravitational field. The special theory of relativity ignores gravity. The general theory includes gravity. And so what Einstein discovered was that space and time are a little different than what most people think they are. They're not sort of absolute and the same everywhere. Clocks don't. Our natural expectation is to think that clocks all tick at the same rate if they're well constructed clock. Okay, you got a good one. You got a Rolex, and it's going to take a licking and keep on ticking, right? The assumption is that no matter how you move, it doesn't affect the rate at which time flows. And the effect indeed is so small that we don't notice it in our everyday lives. But Einstein was able to figure out rationally from really just two observations that time is affected by motion. The flow of time, the rate at which clocks tick, is affected by motion. And also lengths are affected by motion. And so, how thick you are depends on how fast you're moving. That's kind of interesting. And again, it's not something we would notice in our everyday experiences because the effect is very small. It's not until you get up to a substantial fraction of the speed of light that the effects become significant. But that's really what it is. It's the physics dealing with very, very high speeds or very intense gravitational fields. One of the peculiarities that was discovered in the late 1800s is that the speed of light, no matter how you measure it, the round-trip speed of light is always 186,282 miles per second. And that's very peculiar. I want to give you an example of this. Suppose that you're in a car and you're driving 50 miles an hour, and somebody in the back seat takes a baseball and throws it, and they're capable of throwing a baseball at 50 miles an hour, and so they throw it out the window. Now, someone on the sidewalk would see that ball traveling at 100 miles an hour, wouldn't he? Because it would be the speed of the car plus the speed of the baseball. It would be 100 miles an hour. That's called the Galilean velocity addition theorem. Okay? You just add the velocities. But what's peculiar is light doesn't work that way. If I'm traveling down the road at half the speed of light, and I turn my headlights on, and they're moving the speed of light faster than me, which is c, I'm traveling at half c, you'd think somebody on the sidewalk would see the light traveling at 1.5 c, 50% faster, but he doesn't. Somehow he sees the speed of light as c faster than him, whereas I see the speed of light as c faster than me, even though I'm moving relative to him. Very peculiar. And Einstein realized that the resolution to that paradox is entailed by the fact that my clock doesn't tick at the same rate as someone on the sidewalk, and so the way I measure time's different, and lengths change, and so the way my rulers are not the same as a person's who's stationary on the sidewalk. And the thing that's surprising to people is when you're moving, you do not notice any of these effects because everything shrinks together. Okay, and so you might say, well, this roller seems just as long as it used to be. It's still the length of my arm, but that's because your arm is also shrunk in that direction, and so on. So everything moves together. Your time might be slowed down, and so you're moving very slowly, and your clock is ticking very slowly, but you don't notice it because your brain is slowed at the same rate your watch is. And so everything slows together. And so you don't notice the effects in your own car or in your own spaceship or whatever you're in that's moving at some substantial fraction of the speed of light. But somebody watching you with the telescope would notice that inside your chamber there, you're moving very slowly. And the faster you get to the speed of light, the slower and slower time flows.
All right. Since motion affects the passage of time, is that why car clocks never keep time?
It's not. The effects of relativity on the slowing of time are minuscule, and they're not something you're ever going to see. Because in order to see a 1% time dilation, in order for a clock to be ticking 1% slower than a stationary clock, you would have to move at 14% the speed of light. And none of you have cars that can get up to 14% the speed of light. By the way, that would be about the equivalent of if you were to travel around the Earth in 1 second. Can you imagine that? Traveling around the Earth in 1 second, you'd be traveling at about 14% the speed of light. So if we put a clock on Superman and we have him fly around the Earth in 1 second and he comes back, there would be a 1% difference between his clock and my clock. He would have experienced time dilation. So at ordinary speeds, at 50 miles an hour, the effects are negligible. You can't measure them. And you might say, well, how do we measure them at all? And the answer is using atomic clocks. That's how it's been measured. One of the first experiments to measure time dilation had airplanes fly around the world in opposite directions. And because the Earth's rotating, the plane that's flying westward is effectively stationary. The Earth's just rotating underneath it, whereas the other one is moving substantially. And even though it's not even close to 14% speed of light, nonetheless, the atomic clocks could measure even the very small difference. But unless your car has an atomic clock, you're never going to notice. You're never going to notice any difference. Car clocks aren't very accurate because they're not very well built. That's all it comes down to. Yeah.
So while you are moving, while you are in motion, while all of us are in motion, you are technically, time is traveling slower for you.
Yeah,
you are thinner and shorter, and distance has shrunk. Yeah. But so negligible that we never notice it, never can notice it.
That's right. That's right.
But it's a real phenomenon nonetheless.
It is. And gravity is another factor too. Gravity also slows the passage of time. And so the fact that we're sitting here in a gravitational field as opposed to in deep space causes our clocks to tick just slightly slower. And therefore you're aging very slightly slower than if you had a twin who lived out in space in 0G, you would age slightly slower. And I figured out the difference one time. I thought, what is the difference of the effect? And the answer is, if you lived to be 70 years old, you would gain an extra 2 seconds for living on the Earth in a gravitational field. That's the difference. It's tiny. It's tiny. So as you move closer and closer to the speed of light, since time slows down, you age very slowly. But from your perspective, it doesn't seem that way. It seems like time's flowing normally. But from your perspective, as you're moving very fast, you're always allowed to consider yourself stationary, you see. I mean, we don't feel like we're moving, do we? We're in this room, we're on the Earth, the Earth's rotating, and we're moving at 700 miles per hour relative to the center of the Earth in a easterly direction. And then we're orbiting around the sun at 67,000 miles per hour. You don't feel that, right? Because it's a smooth motion. So the person who's in the spaceship, from his perspective, it's the universe that's moving backwards at a substantial fraction of the speed of light. So from his perspective, since things shrink in the direction of motion, that star that was very distant is now not so distant because the universe is compressed in the direction of motion, interestingly. And so what happens, let's say it's a star that's, say, 4 light years away. Alpha Centauri, the nearest star, is 4.3 light years away. So you'd say, well, it's going to take at least 4.3 years to get there because we can't move faster than the speed of light. We can only move slower than the speed of light. So I move up to a very high speed, as closest to light as I can get. The person on the ship would be able to make the trip in, say, a couple of months. Because from his point of view, the universe shrank in the direction that he's traveling, and so that it didn't take very long to get there. Now, a person on Earth would say, no, the reason you were able to make that trip in what seems like 2 months is because your clock was running very slowly. And so they both agree, everybody agrees that they're able to make the trip the astronaut is able to make the trip aging only a couple of months. They disagree on the explanation for why, because the explanation is relative to the person's point of view. So that's where it gets its name.
So twin astronauts, one stays on Earth, one gets in a ship and heads off to Alpha Centauri, makes the trip there, and comes back. What happens?
So if he comes back and meets his twin would have aged 8.6 years, whereas the astronaut would have aged barely, 4 months, say, depending on the speed. So the twins are now different ages. So very interesting.